In this video, I'd like to talk about memory. Now, memory in a computer is typically the word that we use to refer to random access memory, as opposed to sort of the persistent memory that's on our hard drives or our solid state drives. That is still technically memory, but typically the nomenclature when people say memory, they're typically referring to our RAM, our random access memory, the volatile memory that when our device turns off, we lose. So one way that I like to think about memory is as a large pool of zeros and ones, right? A whole bunch of zeros and ones. Our memory has memory addresses associated with it. So if we start at the very, very beginning, this would be memory address 0. And memory address 0 would point to an individual byte of data, 00101001, something like this. And then memory address 1 would point to another byte of data, 11000100. Obviously, this is an incredibly simplified version of what memory is actually like, but this is a good way to think about it. Our memory addresses just continue counting up, and they get really, really large. Right? There's a lot of bits and a lot of bytes within our RAM sticks, and now we're talking about 16, 32, 64, and larger gigabytes of memory, right? So we need to support really large memory addresses. These numbers, just the addresses, are going to get really large. Typically, these memory addresses are written in hexadecimal for that exact reason. So you'll see memory addresses written as 0xFFA231 or something similar to that, right? In hexadecimal format. And this points to, another byte of memory with just zeros and ones. Now, whenever I declare a new variable in code, if I do something like this, int health, this is a command in my programming language that tells my computer what to do. And by writing a command like this, int health, and declaring this variable, I've asked the computer for space in order to store an integer. And then the other thing that I'm doing is I'm saying, whenever I want to refer to that space in memory, I'm going to call it health. Now, under the hood, as part of the operating system and its interface with the hardware, what it's going to do is it's going to give me the space in order to store this integer that I'm looking for. So what's going to happen in a very hand-wavy way is it's going to say, you know what, there is a free spot in memory here at memory address 0x2AB331. This is a free spot in memory. No one's currently using this byte. This byte here looked like this previously. Whoever was storing data at this position, it's still like that. No one's ever changed it since the last person used it. So that's what's going to be there. Now, the next thing that's going to happen is it's going to say, well, actually, this integer is probably a 32-bit integer, which means that you actually need 32 bits. Well, each of our memory addresses in memory is pointing to a specific byte. You need more than this. You need 4 bytes, which are your 32 bits. Now, I'm just making up what other data could previously be in in this memory. Something like this. And this whole section is going to be reserved for my value of health, right? So you can kind of think of that this value here, health, has just been given this entire block of memory, which is 32 bits total. Now, the interesting thing about this is because memory is addressed per bytes, that this variable health is actually taking up 4 memory addresses. Here's memory address 2AB331, and then 2AB332 is this byte, and then 2AB333 is this byte, and then 2AB334 is this byte. These are the memory addresses to each of the bytes within this variable health. Now, this is a really important concept that could be used later as we start to manipulate these bits and get into some of the optimizations and things we can do within memory. So now it still has this garbage data in it, and in some languages like C#, this would actually be cleared out nicely for you. It would just give you a straight value of 0. You clear all these out and set them all to 0. In a language like C or C++, it doesn't do that. By just declaring a variable like this, it's going to give me access to this memory. It's going to allocate this memory for me. So now this is reserved for my health value, but it's not going to clear it. So that's why it's very important to initialize all of your variables. This is actually 2 steps that it's going to do here. The second thing that's going to do now is it's going to go and clear all of these bytes and set them all to 0 because I've assigned my health value. I've initialized my health value to 0. So it will go and clear this memory for me. And now it'll be equal to something that looks like this. Just a series of zeros. This is fundamentally how variables, when you initialize them, are stored in memory. And the interesting thing to me is that every single variable in all of your code and in every single program that your computer is running at the same time is all stored within this giant pool of memory. So what data is stored at the next position over? This is your health, but what's stored at this position or this position? I don't know. It could be something with a different program. It could be something in your program, right? This is part of the job of the operating system to help figure out where to put memory in individual pieces of data.